Hello everyone, welcome to this video on thin linear wire antennas, one of the most fundamental topic in antennas. So antenna plays a very important role in transmitting information from source to destination and even from in reverse process, that is either the antenna can act as a transmitter as well receiver in transmitting, receiving electromagnetic energy. So thin linear antennas are made of conducting wire whose length is measured in terms of wavelengths. Generally, they are in very small in size. Even the diameter also less than 1/100th of the opening wavelength, allowing us to assume that the current flow only along the length of the wire. The wire antennas are among the simplest and most widely used antennas because they are easy to design, low in cost, lightweight, efficient for transmitting and receiving electromagnetic waves. Some are the basic antenna elements of thin wire antennas. Here we can see on screen is Hertzian dipole, short monopole, half wave dipole, and quarter wave monopole. Hertzian dipole is a short linear antenna in which the current element along its length is assumed to be constant. Current is constant. Distribution of the current inside the wire. And the short dipole is a linear whose length is less than lambda by 4, and the current distribution is triangular in the sense with respect to the center of the wire, it is a maximum in current distribution. At the end points, it will be almost zero. Then the short monopole, it is also a linear wire whose length is less than lambda by 8, and the current distribution is also triangular here. Next, for half-wave dipole, length is equal to lambda by 2, and the current distribution is assumed to be sinusoidal. It is usually used for the half-wave dipole. We'll use a center feed. And the last one, the type is quarter wave monopole. The linear, it is also a linear antenna whose length is lambda by 4, and the current distribution is assumed to be sinusoidal, same. It is fed at one end with respect to earth. Now, let us see the Hertzian dipole, or the another name for the Hertzian dipole is a small current element or infinitesimal dipole. So the current element is an infinitesimal linear wire. It's a linear wire whose length is very small. So in terms of dimensions of the wavelength, it is much less than in terms of wavelength. It is denoted as L is much less than lambda. That the current element is positioned here. In the figure, you can see the dark portion is being placed along the z-axis. It seems that the current is flowing inside the small element, and current is assumed to be constant along its length, and such that we have placed the antenna that is 50% of the length on positive z-axis and remaining portion in the negative z-axis. And at some point P, we have been calculating different parameters, that is electrical field lengths, magnetic field potentials, vector potentials, and the power, radiation resistance, so that P is located at some far distance or with respect to the center of this coordinate system. And the phi represents azimuthal angle, which is a horizontal plane. And this phi is being measured, the projecting point of P onto the xy plane. Then phi is measured. And with respect to P, the vertical plane, theta azimuthal angle is measured here. And the right side figure is shown the same current element is placed with respect to spherical coordinate system. We can see that here, once again, the shaded portion is a small differential element, the shaded portion, and theta, phi are these three are the spherical coordinates components are theta, phi. R is the distance from the center origin to the field point, and ER, E theta, E phi are the electric field components. And similarly, we can have the representations of HR, H theta, and H phi. That is, the magnetic field components also can be considered in these three coordinates, HR, H theta, H phi. In order to obtain all these three, first of all, we need to obtain the we need to obtain the vector potential A in order to get the field components of electric and magnetic. So here, the source only carries a current I, E and IM. That is a electric current and is when magnetic current. And the potential function is A. We can write for the potential function as A bar is equal to mu by 4 pi for the integral I of x, y, z into e power minus jkr by r into dl. Here, this vector potential is representing the coordinates with respect to the source, and capital R is the distance from any point on the source to the observation point. And with respect to this, we can identify the distance R is the magnitude from the origin. So that capital R can be written for the magnitude, we will get x square plus y square plus z square. With representing x, y, z or x dash, y dash, z dash. If as x dash, y dash, z dash, if we made that it is the origin for the infinitesimal dipole, then we can get x square plus y square plus z square. And we can get the final vector potential equation for this infinitesimal dipole. We can write as EA of x comma y comma z is equal to unit vector AZ into mu I naught by 4 pi r into e power minus jkr for the length of the dipole, that is the infinitesimal dipole or a small current element, integrating from minus L by 2 to plus L by 2 into dz dash is a value. If we make the total length as L, then from the figure we can see that it is length is being divided from the minus L by 2 to plus L by 2. With that consideration, we can get the final vector potential integrating the value. Then you can get AZ bar mu I naught L by 4 pi r into e power minus jkr. Here, the vector potential, you can see the representing with the coordinates x, y, and z. These are the Cartesian rectangular coordinates, but the practical considerations of the thin linear wire antennas is being considered for the spherical system, which is being denoted with r, theta, and phi. So our first aim is to convert vector potential into spherical coordinates. And the resultant vector potential we can see here is representing the potential only in the z direction. As from the figure, we can see the element is placed on the z-axis and the current is direction along the z-axis. So we have the vector potential is also only Az. With this representation, we can conclude for the vector potential as Ax and Ay terms will be 0. And only the component of the vector potential Az will be exist. And let us transform the vector potentials x, y, z into r, theta, phi spherical representation. For that, we will write transformation representation ar, a theta, a phi in matrix form, that is equal to sine theta cos phi and sine theta sine phi cos theta. So as it is three terms r, theta, phi, we will get the matrix representation is in 3 by 3 form, that is 3 rows and 3 columns. So according to that, we are going to write this value sine phi cos phi 0, the last row, multiplied with the rectangular coordinates ax, ay, az. From this, we can get to represent that the value of ax, ay turns to be 0 as the vector potential exists only in the z direction. Substituting this and multiplying this 3 by 3 matrix with 3 by 1 matrix, we can get the final values of vector potential ar, a theta, and a phi as cos theta az minus sine theta az and 0. I'm writing that multiplying the 3 rows, 3 columns with 3 rows, 1 column matrix, we can get the values of ar, a theta, a phi is a final spherical coordinates representation for the vector potential A. So from this, the vector potentials in spherical coordinates obtained in terms of x, y, z. With this consideration, we will substitute the az value in this terms. So let us rewrite the values of vector potential in terms of spherical coordinates. Ar is equal to az cos theta, that is equal to mu I naught L by 4 pi r into e power minus j k r into cos theta, and a theta is equal to, we obtain minus sin theta az. So for that, we'll write minus az sin theta, that is equal to minus mu I naught L by 4 pi r into e power minus j k r into sin theta. As the terms for the A5, there is no value, so that has been considered as a 0 from the previous slide we have seen with the evaluation. Now, using this vector potentials, we have to obtain or derive the magnetic field strength and similarly electric field strength. So we start with the magnetic field strength, that is H. So for this, we will consider the Maxwell's equations. So that is, with representing magnetic field, we have a notation B bar is equal to mu H bar. So here, as we read H, make it to the left hand side. So 1 by mu into B bar. So there is a relation between B bar and, that is, a magnetic field intensity, magnetic flux density vector potential with respect to that B equal to del cross A bar. Substituting this here, we can get the equation of the magnetic field intensity in terms of A bar. H bar equal to 1 by mu into del cross A bar. Now, mark this as equation number 1. So let us elaborate this del cross A bar as the matrix representation in terms of Cartesian spherical coordinate systems. Then we get the equation as del cross A bar is equal to 1 by r square sine theta with the unit vectors r a theta, r sine theta a phi, with the differential vectors dou by dou r, dou by dou theta, dou by dou phi, and the last row will be ar with respect to vector potential r a theta, r sine theta a phi. So if we expand this vector potential with rows and columns using applying determinant for this 3 by 3, then we can get the expanded term will be representing as del cross A bar is equal to 1 by r square sine theta. So I am expanding with respect to the previous slide, determinant 3 rows, 3 columns. So first we get AR component into dou by dou theta into r sine theta a phi minus dou by dou phi into r a theta minus r a theta into dou by dou r into r sine theta a phi minus dou by dou phi into ar. The last term as plus r sine theta a phi into dou by dou r into r a theta minus dou by dou theta into ar. So this is the term we get after expanding del cross A bar using the spherical coordinate system. So here, from the equation and from the figure, we can get that the Z is, the current element is placed along the Z axis. then using the symmetry of the problem that there will be no variations in the phi. So the equation is here is in spherical coordinates as that no variations in phi component that results in the unit vector AR and A theta will be marked as 0. So with that consideration that the complete term AR, the first term will be 0, the second term will be marked as 0. Then we can get the simplified equation for the del cross A bar is equal to 1 by r square sine theta into r sine theta into A phi. Dou by dou r into r A theta minus dou by dou theta into AR. So this is the equation. So here there are terms, some terms are cancelled, sine theta cancel, one r is also cancelled. So then we can get the value of del cross A bar is equal to A phi by r into dou by dou r into r A theta minus dou by dou theta into AR. This is the final expression that obtained for del cross A bar. So in earlier we have written the magnetic field equation, strength 1 by mu is equal to 1 del cross A bar. So we are going to substitute the final equation of del cross A bar here in equation 1. Then let us see, we get the del cross A bar has only the component of phi. There are no r component and theta component. So in result, you have the magnetic field components HR will be 0 and H theta also will be 0, as the vector potential is reflecting only the phi component. So let us obtain the final H phi component using the vector potential as substituting this in equation 1. Then we can write the field component of H as a only phi, that is H phi is equal to 1 by mu r into dou by dou r into r A theta minus dou by dou theta into AR. This is the value. And then here substituting A theta and AR, which were derived earlier for the vector potentials. From that, we can copy and place it here, AR, A theta components in magnetic field. So then we can get 1 by mu r into dou by dou r into r minus mu I naught L e power minus jkr into sine theta by 4 pi r minus dou by dou theta of mu I naught L e power minus jkr by 4 pi r into cos theta. So that is equal to, after evaluating certain terms, that is a differentiation, if we apply that in the first term, the dependent term is only as e power minus jkr. In the second term, the only dependent term is cos theta. For this cos theta, if we apply differentiation, we can get minus sine theta. So that minus will be reflected if the term will return plus. And here e power minus jkr reflecting the terms e power minus jkr into minus jkr. That minus jk will reflect this sign as plus. Then rearranging the terms, those things as 1 or 2 steps we can proceed. Then 1 by mu r into e power minus jkr into jk mu I naught L sine theta divided by 4 pi plus mu I naught L e power minus jkr into sine theta divided by 4 pi r. So taking the terms, certain terms common. So then finally we can write h phi is equal to j k I naught L sine theta divided by 4 pi r into 1 plus 1 by jkr into e power minus jkr. This is the final term. So as said earlier, so we have the magnetic field strength only in phi. So then HR is 0 and H phi is also 0. So this is the derivation that we have been obtained. Magnetic field strengths for the small, current element or infinitesimal dipole or Hertzian dipole. Now let us see now electric field strength for the same current element or infinitesimal dipole. Electric field strength. So notation is representing E bar. So in Maxwell's equations, we have the term is E bar is del cross H bar equal to J bar plus dou D bar by dou T. So here we'll consider the J bar, that is a current density, is considered to be 0. Then here dou by dou T is in time domain. If we will convert this time domain into frequency domain, that is dou by dou T from the Fourier transform, it will become as a j omega. And your d bar will be is in terms of electric field is a epsilon e bar. So if we rearrange these terms, then we will get del cross h bar is equal to j omega into epsilon e bar. These terms we will get. So our required term is e bar. So e bar is equal to 1 by j omega epsilon into del cross h bar. So now we have obtained the term of E bar in terms of H bar. So earlier we have the terms A bar utilized to evaluate H bar. Now we are going to evaluate E bar using H bar. That we will see in another part of the video. Thank you.